Hey everyone, this is Smash here. We're going to be doing the 2022 higher paper 1 for physics. Yeah, I really should get around to doing the higher biology paper 2, but I'm really lazy and physics is coming up, so I'm kind of terrified. Anyway, moving on. Data sheets, you know what to do with this. Sometimes you get called to do some numbers here. Yeah. Anyway, we'll move on to question 1. A ball is thrown vertically upwards and falls back to its starting position. The acceleration time graph represents the motion of the ball. And as you can see here, this is as expected, the ball is constantly getting decelerated by gravity. Which of the following velocity time graphs represent the same motion? Well, let's have a look for all these. So remember, acceleration is constant, it does not change. We're looking for a straight line with a constant gradient. And already I can see that most of these are quite rubbish, and I've forgotten to open this in annotate, which is a bit of a bad move by my part, but I'll continue on. But as you can clearly see here, there is not, we can get rid of all these here. They've all got lines that diverge and they change gradient. So you just move on to A and D. And, well, if it's decelerating, then the velocity is going to go down. It's not going to go up. So it's got to be A. I will move on to 2. A student uses the apparatus shown to determine the acceleration of a trolley as it moves down a ramp. The trolley is released from rest at point P and moves down the ramp. A card attached to the trolley passes through the light at point Q. Time for the car is going to display on the electronic timer. The electronic vehicle's acceleration A is determined using the relationship, which you'll probably find in your, this will be familiar for you. It's one of the two equations. The student makes the following statements about the terms U, S, and V. U equals 0 meters per second, S equals the length of the cards, and V equals the distance between P and Q and divided by the time displayed on the timer. So, let's go through these. Well, we're calculating acceleration here, obviously, and well, it says the trolley is released at rest at point B. So that means its initial velocity is going to be 0 meters per second. S equals the length of the card. Now, this is incorrect, unfortunately, because this is the amount that the S in this case is the amount that the object is moving during the acceleration. And we're measuring as it accelerates down here. So S would actually equal the distance between the light gate and the card. So 2 is garbage. V equals the distance between P and Q divided by time displayed on the timer. That is also bad. V is the instantaneous velocity that we get here. So actually, you could calculate V as, V equals d over t, but d in this case is actually the length of the card. So this student has clearly got the length of the card and the displacement of the object mixed up, but time displayed timer is correct. So this leaves us with 2 rubbish ones and 1 good one, so it has to be A. Moving on to 3. A spacecraft unloads cargo on the surface of the moon. The gravitational field strength on the moon is 1.6 Newton kilogram per kilogram. A package of mass 3 kilograms moves down the ramp. Components of the weight of the package acting parallel to the ramp is what? So remember parallel, that means that it's the force acting this way, not the force downwards the weight. This means that we're going to have to choose our force equations. Okay, so what we're going to do here is go, so the force we want is total force, and then we can think about it for a second. So if we had an angle of 0 degrees, right, that's just going to be a straight line, right? So there's not going to be any movement. But if we had a angle of 90 degrees, that means that it would be the full weight be moved down. So if we want something that starts at 1, it starts at 0 and then moves up to 1, well, that looks like a sine graph. So let's go and use sine. Okay, and then we're just going to go, then we need to calculate the weight of this. So we can do that with W equals mg. I've done this in a slightly terrible order, but here we are. And well, what's g? Tells us 1.6. So I'm going to pull up my recalculator here. So 1.6 times 3. That gives us 4.8. So that's 4.8 newtons. And then we're going to go 4.8 newtons times sine 34 degrees. Okay. So I'll just quickly do that. What do we get? We get 2.68 and some other numbers. And if we round that up to 2 decimal places, we'll get 2.7 newtons, right? And oh, look at that. That's B right there. Moving on to 4. 2 blocks are suspended from a ceiling by ropes as shown, which row on the table shows the tension in the rope at point X and the tension in the rope at point Y. Okay, well, let's actually go through this. The tension of the rope at point X will always be higher than point Y because it's pulling not only the 15 kilogram block but also the 12 kilogram block. So doing that, without doing any maths, let's go and eliminate some that just cannot be possible. So, well, C's garbage. And yeah, that's it so far. D does not look likely, can't be, but it's always good to eliminate them as much as you can. So, how are we going to calculate this? Well, Y is just going to feel the effects of the 15 kilogram block, and we're going to assume this is on Earth. Yeah, if it doesn't tell you it's on another planet, you assume it's on Earth. The gravitational field strength will be 9.8. I'm sorry for my atrocious handwriting. So I'll just go and quickly calculate that. We get 147. Now, you might not see 147 on here, but it does look pretty similar to this if you round up to the nearest 10. Right, so E's looking pretty likely so far, so we've all eliminated C. But let's just prove it. Let's do tension at point X. So X is pulling down a weight of combined 12 and 15. So we're going to go add 12 and 15 together. What do we get? Well, we get 27 kilograms. And plugging that into our equation, 27 times 9.8. What does that get us? Gets us 264.6. If I could remember how to do it. And again, if you round that to the nearest 10, you get 260. So yeah, we've just proven that it has to be E. Cool. Question 5. During an experiment, a student inside a lift stands on a Newton balance. The mass of the student is 50 kilograms. Lift accelerates upwards at 1.2 meters per second. Reading on Newton balance is what? So Newton balance, remember, that shows a scale that measures it in newtons rather than kilograms. So how are we going to figure this out? Well, we want to get a force diagram on the student. So let's go and calculate what the weight component of there will be. So, yeah, their weight if they were just standing in a regular environment, not on a lift. No, obviously it would be 9.8 because we assume they're on Earth. There's not many students in space, I hear. So, what do we get if we do that? We get 490. So this will allow us to eliminate some C. Can't be 490 because it's in a different environment. And what will we expect to happen? Well, if it's accelerating upwards, that means that the student will be pushed into the ground more, right? Because the lift is applying a force on the student. Okay, so we're going to expect it to be higher. So it's going to be D or E. So we don't think it's going to be B or A. Okay, so what is 1.2 meters per second squared? Effectively, that means that you're going to add that onto 9.8. So basically, that means if you had a theoretical lift, like a rocket ship in space, that it just accelerated at 9.8 meters per second squared, you would feel like gravity. But this is on Earth, so we're going to add it to regular gravity, right? So do the proper equation now. 50, and we're adding the acceleration on. So 1.2 plus 9.8, that is 11. And then we can just do this in the head. I don't want to dumb it down too much. We get 550 newtons, which is D, the correct answer. Water flows at a rate of 1.0 times 10 to the 6 kilograms per second over the Victoria Falls. Victoria Falls are 120 meters high. The total power delivered by the water falling through 120 meters is what? Okay, well, what we're going to do here is use calculate the gravitational potential energy, which is represented by this formula. So E is the potential energy, M is the mass, G is the gravitational field strength, and H is the height. So of course, mass, we've got it as 1.10 to the 6. Gravity, which this is on Earth, there's no waterfalls in space, and 120 meters. So we're just going to times that all together. And we're going to end up with this number. 1.176 times 10 to the 9 joules. Now remember, this is per second, which means this is amount of joules per second, otherwise known as power. You could actually do the power equation, but T would just be 1. So you would just get this number. Okay, so where does that leave us? Well, again, SQA has weird rounding things, so I'm going to round it up to 2 decimal places, which is 1.2 times 10 to the 9. And oh, look at that. That's right there. Remember, units are in watts, not joules, because it's per every second. We've just calculated the amount of joules that you get in 1 second, so it'll be the same as the wattage. So yeah, I'll make that a bit better. Oh my god, I'm not very good at drawing stuff today, am I? Right, that'll do. And we're going to move on to 7. A spacecraft passes the Earth at a speed of 0.4 c. C is the speed of light, so 0.4 times 3 times 10 to the 8 meters per second. A light in the spacecraft pulses on and off. A passenger on the spacecraft measures the time between the pulses as 2.5 seconds. An observer on Earth measures the time between the pulses as what? So this is going to be a time dilation question. So this is probably going to have you pull out your relationship this time, but got these two relativity questions. This one's for time, this one's for length. So we're just going to copy this one in. Not that tab. So T prime equals T over root 1 minus V over C squared. And we're just going to plug in our numbers. 2.5 over, now I'm going to replace this V over C term with 0.4 because that's just what it is. You're dividing, you're seeing what fraction of the speed of light is essentially with that. So it'll be 1 minus 0.4 squared, and well, what do we get with that? 2.5 divided by, put some brackets in, 1 minus 0.44, but that is g squared. Yeah, this is going to be a bit weird. And then do that, and then that. That gives us 2.72, I will round it up to 3 seconds. And there we go. So we're thinking that this will look like the correct one. And again, we can go and eliminate some of these. So remember, time effectively slows on fast-moving objects. So that means that they will see this. We will see it. A stationary observer would see it as taking longer. So and it can't be the original thing. So we can eliminate A and B, and we just need to narrow it down from there. Okay. Number 8. A student makes the following statements about the expanding universe. The evidence supporting the existence of dark matter comes from the estimations of masses of galaxies. The evidence supporting the existence of dark energy comes from the accelerating rate of the expansion of the universe, and the peak wavelength of radiation emitted by hotter stars is longer than that for cooler stars. Okay, so let's go through these. Yes, first one is correct. Dark matter comes to estimation of the mass of galaxies. They looked at galaxies, saw the mass that they could see with like visually in optics, and then they did calculations of like gravity and whatnot, and found they were spinning too fast. So they would tear themselves apart if they didn't have extra gravity produced by dark matter, which we can't see. Evidence supporting the existence of dark energy comes to accelerating. Yep, dark energy magically somehow just expands out, creates space between objects. But peak wavelength radiation emitted by hotter stars is longer around cooler stars. Well, higher, lower wavelength radiation is shorter for higher energy. So, and it's hot, heat is energy as well. So you expect hotter stars to actually emit shorter wavelengths, which they do. Red giants are cooler than blue giants. So that means 3's garbage. So it's 1 and 2, so it'd be D. Moving on to 9. A police car is travelling at a constant speed of 31 meters per second towards a stationary observer. The siren of the car emits a sound with a frequency of 820 Hz. The speed of sound is 340 meters per second. The frequency of the sound heard by the observer is what? So we're going to be using Doppler equation for this, which is this bad boy here. Now, it is approaching a stationary observer. So that means that, I've already forgotten my, yes, okay. That means we're going to be minusing. Now, source frequency tells us it's 820. And then we're just going to fill in stuff. So 340 minus 31. What do we get? Oh boy, this will be a lot of brackets. Okay, so this is, I've just calculated this term, so we just need to calculate 820. What do we get? 902 Hertz. And we should look at that. That's E. And again, we can think about if it's moving towards our observer, the frequency is going to increase because you're pushing the crests together, right? So that means that A and B are garbage. It's going to be different because you're moving, so it has to be D or E. You just need to work out from there. A proton enters a region of magnetic field as shown, and unfortunately, this is going to be slightly difficult to show you in real life because this is using the right and left hand rules. The direction of force exerted on the magnetic field as a proton as it enters the field is what? So you're going to position out your hand. Now, there are a couple of ways you can do it. You can either use the right hand rule for everything, or you can use the right hand rule and left hand rule depending on what thing is. I'm going to use the left hand rule because it's a proton. You can use right hand. You can use the right hand rule for the electron. So your forefinger is going to be your index. In other words, is the magnetic field. What way it's pointing. So I'm going to point my finger to the right, forefinger, and then I hold my thumb at 90 degrees and my finger at 90 degrees. I'll have to show you a thing else, but that means that my middle finger is pointing downwards and my thumb is pointing towards me. So my middle finger is the direction of charge, and because this is a proton, I'm using my left hand. If I could use the right hand, but I have to make sure my charge finger is in the other direction, which is a bit difficult to kind of work around. So left hand's a bit easier for this. Okay, and then thumb is movement. So that means that it's coming towards me, so you can say it's out of the page. If you want, I could do a proper tutorial on this because I know for screen recording it's quite difficult to tell. The masses of free particles are as shown. But you've got an electron, we've got a proton, and we've got the Higgs boson. how many orders of magnitude is the mass of a Higgs boson compared to the mass of a proton? So the way we're going to do this is you can kind of just compare it and be like, okay, it's about 2 orders of magnitude. Which, yeah, it is the correct answer if you just want to look at that. But just in case, let's go and divide them both, right? So I'm going to go 2.22 and then 25, and then divided by 1.673. 27. What do we get? We got 132.7 or whatever. Well, it doesn't really matter. That's 2 orders of magnitude, so to speak. Hey folks, this is Mash from the future, because past Mash completely flipped up this question. Like, I don't know how I got this that badly. But yeah, this is question 12. A proton consists of 2 up quarks and a down quark. A student makes the following statements about protons, either the baryons, the hadrons, or the fermions. Which of these statements is/are correct? So, get the obvious one out of the way. Fermions, they are matter particles, so they make up quarks and anything better than quarks and leptons. So leptons are like your electrons and quarks are your fermions. So yeah, protons are fermions because they're made out of matter particles. Ain't that brilliant? So then for baryons, they're particles made out of exactly 3 quarks around about. So that's your protons, your neutrons. And well, look at this. That's 2. That's 1. 2 plus 1. You're not going to believe this, guys. 3. So yeah, baryons, totally great. And then last one, hadrons. Well, hadrons are just composite particles made out of quarks and gluons. They're basically just quarks. And well, yeah, we put some quarks together. Of course, it's going to be hadrons. So yep, all of these are correct. So it's E. 13. The following statement represents part of a radioactive decay series. Nucleus X undergoes alpha emission to produce nucleus Y. Nucleus Y then undergoes beta emission. Nucleus X is what? So we're going to have to work backwards here. Remember, beta emission does nothing towards the mass, right? So we're just going to have 214. I'll write this somewhere else. It might be a bit. I'll say Y equals whatever. Doesn't change the mass. It does increase the atomic number. So the Y would actually be 82 because it increases up to 83. Cool. Okay, and then we go back to alpha emission. So alpha emission decreases the mass by 4 and the proton, the atomic number, by 2. So that means we'll have to add 4 there. So we go up to 218, and then it would be 84. Okay, so we're looking for something with 218, 84. Here we go, 218 polonium. So there we go, the answer is C. The following statements represents a nuclear reaction. So you've got plutonium, and it's splitting into uranium and helium. The total mass of the particles before the reaction is this long number. The total mass of particles after the reaction is this long number. Energy release reaction is what? The way we're going to do this is we're going to take these numbers away. You see there's a very small difference between them. That small difference is converted directly into energy, which is how we're going to calculate it. So yeah, this is just kind of a shove in a calculator and hope you're the best question. So not much to do here except watch me type numbers in. Boom, and we'll get this infinitesimally small number, 1.1 times 10 to the 29. Remember, E equals mc squared, most famous equation ever, probably. So we've got the mass, C is a constant, it's 3 times 10 to the 8, speed of light. So I'm just going to go 3 times 10 to the 8, and then square it, see what we get. 9.9 times 10 to the minus 13 joules. Let's see if we got that. Oh, there we go. It's D. Right, 15. The radiance of light into the thermal surface from a point source is 20 meters at 20 watts per meters squared. The distance between the point source and that surface is 5 meters. The point source is now moved to a distance of 25 meters from the surface. The radiance of the light is now what? So what we work out here is using the irradiance formula. So I1 distance 1 squared equals I2 distance 2 squared. So radiance of point is 20, and then it's originally 5, but then it gets moved to 25 meters. And all we're going to do here is do this and then divide it by 25 squared. Excuse me. So I'll just quickly do that. I'll get out of this. So we get 500. And then divide by 25 squared. Get 0.8 equals I2. So that would be B. Moving on to 16. Light from a laser is incident on the grating as shown. A series of interference maxima are observed on the screen. A student makes the following statements about the interference pattern observed on the screen. Increasing the distance between the grating and the screen increases the distance between the observed maxima. Increasing the distance between the laser and the grating increases the distance between the observed maxima. Decreasing the distance between the slits on the grating decreases the distance between the observed maxima. Okay, well let's think about it. Increasing the distance between the grating and the screen increases the distance between, and that makes sense because effectively you're getting lines jutting out here. So if your screen's further back, these will continue to diverge, right? And you'll get longer further and further apart. So 1 is correct. Increasing the distance between the laser and the grating increases the distance between the observer. Well, that won't, because laser light, it's parallel. All the photons are moving in the exact same direction. They're all parallel to each other, which means this laser could be right next to the grating, or it could be 5 million kilometers away. It won't move. Of course, you know, in real life there's thermal blooming and all sorts, but in magic physics land, it doesn't matter. The laser light will always be the same. So 2 is garbage. Decreasing the distance between the slits on the grating decreases distance. Well, that's incorrect, because smaller gaps will lead to more diffraction, we call it, right? That's just something you're going to have to know, but if you want, you can figure it out. You can figure out, like, well, mh equals d sine beta, so this is the thing, so the angle, the angle is, I guess, analogous to the distance, but if this would stay the same, right, so this is, pretend this is a constant. If we increase decrease this distance, then this sign will have to go up to constant because this is a constant. So actually decreasing the distance between these slits increases the distance between the observed maxima because it increases the angle. So that's really bad. Sorry, that's garbage as well. Which of the statements are correct? Well, it's just 1, so we're just going to have A. Moving on to 17. Which row in the table shows what happens to the speed, frequency, and wavelength of red light as it passes from diamond into air? Okay, so diamond is a more optically dense medium than air, so speed should increase. Okay, so, well, look at that. We've just got rid of over half our responses. Now, what else would change? Well, frequency always stays the same when you're doing stuff around. You know, I don't fire light into a glass prism and it comes out a different color. That's not how things work. Frequency always remains the same, but wavelength can increase and decrease because when you've got V equals F lambda, F remains constant, which means if you decrease V, because you're going for optically distant minimum, wavelength will have to increase to, will have to decrease as well, because F is constant, remember? So I've messed it up there. So when F is constant, V and wavelength are proportional to each other, which means it has to be D. The output from a single generator is connected to an oscilloscope. The trace on the oscilloscope screen is shown. Okay. The Y gain on the oscilloscope is 2 volts per division. The time-based setting on the oscilloscope is 5 milliseconds per division, which gives the RMS voltage and the frequency from the output from the single generator. So RMS voltage, you're going to have to calculate the peak voltage first. You know it's 2 volts per division, so the peak voltage, that's 3 boxes up, so it's 6 volts, because it's 3 boxes, so 3 times 2 equals 6, right? So don't be tempted to do this. This is RMS voltage, not peak. So we're gonna have to do it. Do some calculations. So V peak equals V. Oops. I need to put the root 2 V RMS. So if we just divide the peak setting by root 2, we should get V RMS. So let's just go and do that. We get this number, so VRMS equals 4.24-ish. Okay, and there we go. So we can get rid of all these. We usually figure out the frequency is 25 Hz or 40 Hz. So we want to find the frequency, we want to find the period. The period is when the wave exactly repeats. So you see here, this is one complete wave over 5 boxes. Exactly. And so we know it's 5 millimeters per division. So that means 12 times 5 is 25 milliseconds per division. Which means it's 25 times 10 to the minus 3 seconds. Right? And then to calculate the period, the frequency from that, it's the inverse. So it's 1 over 25 times 10 to the 3. So if I go and do that, and then it's power. Windows calculator never changed and being absolutely garbage to use in every conceivable way. There we go, and we get 40. And there we go, 40 is our answer, so it would be B. Moving on to 19. 3 resistors are connected to a 3-volt power supply. Shown, power supply's negligible internal resistance. Power dissipated in the circuit is what? So what we want to do here is basically combine all these resistors into one mega resistor. So then we can just calculate it easily. So these 2 resistors are in parallel with each other, which means we can use the long-winded equation, yada yada. But I mean, I know a shortcut. These 2 resistors are the same resistance, which means we can replace them with a single resistor of half their resistance. So I'm going to draw the new circuit diagram. This is exactly the same as the old one. Well, I mean, it's obviously different, but it will have the same electrical properties. Right? That's 3 ohms. And then we'll have I know this looks like a fuse, but give me a break here. 9 ohms there. And then we can combine these 2 together to create one big resistor. 9 plus 3 is 12 ohms. And there we go. So we've got 12 ohms and we know it's got 3. So that means we want to find the power. Now power has many different equations, but we've got voltage and we've got resistance. So I suggest we use this one. So P equals V squared over R. V squared is 3. R is 12, so it's essentially 9 over 12. That's 0.75 watts. And would you know it? Let's see. Move on to 20. 6 resistors, each of resistance 5 ohms, connected to a 12-volt power supply is shown. Ooh, we got this big one. The power supply has negligible internal resistance. Which row in the table shows the total circuit resistance and the potential difference between X and Y. Okay, so same principle here. We're going to do some cheaty stuff. If we combine both these resistors here, we can make a single 10 ohm resistor, right? So you can basically pretend that its circuit looks more like this. I'll zoom in a bit. It's a bit more like this with 2 resistors that are both 10 ohms. Right, and then since 2 10 ohm resistors are in parallel with each other, this can actually be represented as just a single 5 ohm resistor, because the 2 10 ohms, because they're parallel, they'll divide it by 2. That's a fun hacky way. So that means we have 3 5 ohm resistors, and so that means total resistance would be 15. Okay, so get rid of these 2. We just need to figure out the potential difference between X and Y. So we know that this is just a 5 ohm resistor, which means the voltage has to be split evenly because it's a straight circuit. So whatever the voltmeter across here has to be the same as across here, because we know this has the same resistance as that, and the same here. So that means it's split equally because it's all got 5, which means if you divide by 12 by 3, what do you get? Well, you get 4. Because when you're splitting the resistance, all these resistors is technically the same, which means that this resistor here would give you 4 potential difference, because then this would also be 4, this would also be 4, this would be 4, and if you add them all together, you get 12. So it would be B. Alright, continue on fourth. A circuit is set up as shown. Excuse me. The resistance of the variable resistor is set to 6 ohms. The loss of voltage due to the internal resistance of the battery is what? Okay, so it tells us the EMF, tells us the internal resistance, and it tells us the resistance. So what I'm going to do is I'm going to go E equals I R plus R. E in this case is 12. And then I, we don't know. We'll calculate that. But we do know it's 4 ohms and then it's 6 ohms. So 6 plus 4. It's 12 equals I times by 10. So it's probably going to be 1.2, let's face it. I'll just prove it. There you go. So I equals 1.2 amps. Fantastic. But we're not done yet. We want the lost volts. So we calculate the lost volts as V equals IR, that is internal resistance. So it's 1.2 times 4. So it would be 4.8 volts, which is B. A circuit is set up as shown. The battery has negligible internal resistance. The capacitor is initially uncharged. The switch is now closed. So this switch here, so this will make a complete circuit. When reading on the voltmeter is 7 volts, the charge stored on the capacitor is what? So again, this doesn't look like this is an outer spot, but this is also a series circuit. So that means that all the voltages across here will have to add up to 12. So if this is 7, then the volt across the capacitor, well, it has to add up to 12. So that means it must be 5 volts. And then we have voltage, and we also have capacitance. So if we go down here, and it's looking for charge, ain't it? I forgot. Yeah, charge on the capacitor. We can use this equation, C equals QV. Capacitance is 220 times negative 6, 10 to the negative 6. We don't know what Q is, but we do know what the voltage is. It's 5. So we times 220 by 5. Oops, flip that up. Get 0.111, which we can translate into good old scientific notation. 1.1 times 10 to the negative 3 coulombs. Oh, look at that. It's C, which is the correct answer. Not too much now. Question 23. A circuit is set up as shown. Ooh, looks to be complicated. The capacitor is initially uncharged. Switch S is closed, so this makes a complete circuit. Which the graph show the potential difference VR across resistor R, the potential difference VC across capacitor C, and the current in I in the circuit vary with time as capacitor charges. Ooh, and we got all these graphs. Okay, well, let's go through. So, whenever you're charging a capacitor, the voltage will be going up, because it'll try and reach, will eventually reach the supply voltage you put in, even if you put in a surprise resistor to have fun with. Okay, so that means we can get rid of all these garbage ones that don't have it going up. Okay, also when you charge a capacitor is that current eventually goes down because you run out of places to store the charge, so eventually you can't push it through there. Means we'll eliminate anything that has the current going up. And yeah, we're already left with E, but what about the voltage of the resistor? Well, remember, supply voltage doesn't change, which means that if the voltage across the capacitor is going up, then that means the voltage across the resistor must also be going down, which is shown. So here we go, voltage across the resistor is going down because voltage across the capacitor is going up, and current is also going down. So E is the answer. 24. Which row in the table describes the current conduction band and the gap between the conduction band and the valence band in an insulator? Okay, so this is an insulator, so conduction band would be unfilled because there's no conduction going on, so we can already go and eliminate the full ones, and now it's just down to bands overlap or not. Bands overlap is a conductor because that means the valence overlaps with the conduction band. So that means that it's already ready to conduct electricity. Very little energy is required because the electrons are already sitting in the conduction band, which means that one's garbage as well. So it has to be C because there's no electrons to be conduct in the conduction band, and there's a large gap, so you need a lot of energy to pump them through. And finally, question number 25. Astronomers use the following relationship to estimate the mass m of a galaxy, where v is the orbital speed of a star in the outer region of the galaxy in meters per second, r is the orbital radius of the star in m, and g is the universal constant of gravitation. A star orbits at the radius 4 times 10 to the 20 meters in the outer region of the triangle in the galaxy. The orbital speed of the star is 120 kilometers per second. Ooh, it's quite fast. And based on this information, the mass of the triangle galaxy is what? And we don't have to do any equations. They're actually quite lucky. So we're just gonna have we don't have to rearrange it because sometimes they make you do that. It's horrific. But we will have to do some minor unit conversions. So remember, it's kilometers per second. So it's actually 120 times 3. And then that whole thing is squared. R is the orbital radius of the star, which it tells us is 4 times 10 to the 20. So this is going to be some huge numbers. And then universal law of gravitation. And remember when I mentioned that data booklet all those years ago? Well, this is where we want to go. Gravitational universal constant of gravitation is 6.67 times 10 to the minus 11 meters cubed per kilograms per second or whatever. So it's 6.7 times minus 18, right? I've just double checked. I'm actually so silly. Sorry, it's very late at night, as I call these. Yeah, minus 11. So yeah, there's no shame in checking back in your data booklet. Sometimes you just got to do that. So 6.67 times 10 to the minus 11. And we're just going to pump that into our calculator. We get this number divided by the universal constant of gravitation. We get this horrific number. Ooh, that's quite massive, ain't it? So yep, it's 10 to the 40 kilograms. And there we go. We have the whole paper 1 multiple choice. Thanks for watching, folks. Make sure to like, subscribe, comment, I don't know. I'll try and read all your comments that I can. But yeah, hope you enjoyed, or at least tolerated me. I'll see you in the next one. Mash out.